Hello and welcome back to DC to Daylight. My name is Derek, and if you've been following along, you know that we've been talking about capacitors. We went through a lot of the theory and I threw some math at you. In this episode, we're going to look at some practical applications. You know, we've got a lot of consumer electronics around the office here I want to take a look at, and especially this microphone, there are a lot of great opportunities to look at capacitors and see what's happening under the hood. So we'll look at some switch mode power supplies, we'll look at linear supplies and a couple other things around here. And I think it's a great opportunity to look at capacitors in their environment. Okay, so let's get right into capacitor applications. Now, there's no way that we can go through all of the capacitor applications, but there are some key ones that I think are important to know about. So we're going to start with those. Things like op amps and active filters, integrators, differentiators, things like that are kind of a topic unto themselves. Just small value capacitors are used to make them do what they do, and I'll probably do another video on that at some point. As it stands right now, we're going to talk about the differences between linear power supplies and switch mode power supplies to start with, and we'll cover some more applications. So basically you have 120 volts or 220 volts somewhere in between, depending on where you live, and the frequency that is delivered to you could be 50 or 60 hertz. Here in the US, 120 and 60 hertz. So we want to step that down usually to operate our lower voltage DC stuff. So we need a nice, clean, stable DC voltage. So we start off with usually a transformer. Okay, so that provides us isolation from the mains circuit, but also steps down our voltage. And then it usually gets fed into some kind of a rectifier. So it could be a half wave rectifier, it could be a full bridge rectifier. The difference between half wave and full wave is if you have a half wave supply, you only get the positive going cycles of that AC waveform. And your frequency is still 60 hertz. So there's a big gap between those pulses, okay? But if you were to use a full wave bridge rectifier, basically that bottom half of the waveform gets flipped up. So your frequency doubles. Now you have 120 hertz, and there's much less of a gap between those pulses. And well, let's talk about capacitors now. So we want a flat DC voltage, but at this point we have a pulsed DC output. So we use filter capacitors to basically filter that and turn it into a stable DC waveform. So what's actually happening? On the positive going pulse, okay, we're charging up our bank of capacitors. We could have one, we could have many capacitors, as we'll see in a second. And as that waveform crests over and starts to decrease and come back down towards zero, right, that capacitor starts to discharge depending on what we have connected to the output as a load. So there are all kinds of calculations to figure out what kind of capacitors you need to reduce the ripple and all this kind of thing. We're not getting into that. Basically, I just wanted to show you the difference between the incoming AC waveform and the pulsed output, okay, and what it looks like when we attach the capacitors. So that's what we're going to look at. Let's go over to the bench. Okay, this is our linear power supply. You might remember this from the Zener diode episode. But basically we have two transformers here that feed into two sets of full bridge rectifiers. That all gets combined into this inductor and then through this capacitor bank. So when we have those positive going pulses, these capacitors kind of fill in the gaps where those pulses start to drop off, right? Where the diodes are turning off. So I just want to show a couple of waveforms. I'm going to show the secondary side of the transformers on the oscilloscope here. I floated the pin of the oscilloscope. Please don't do stuff like this with your oscilloscope, please. Okay, so here is what the output of the transformer looks like, okay? Now, I want to go ahead and measure the output of these bridge rectifiers so I can show you what that pulse DC waveform looks like. In order to do that, I'm going to grab the output of these diodes here. So these are TO220 packages. They're high current diodes and not the little through-hole components that you're used to seeing. So this is what the pulsed DC looks like after the rectifier, okay? So if we compare those two, you can see that the bottom part of that sine wave has been chopped off and basically flipped up to the top side. Okay, so we've doubled the frequency of the input. So just as a comparison, this is a 25 or 30 amp power supply. So this is about 350 watts. I use this for my ham radio gear. Let me just show you in comparison, this is a switch mode supply that is also 350 watts. So just let's pop the cover off that just so I can show you the capacitors in this thing. I don't recommend taking things apart on top of other gear, but we're trying to keep in frame here. So I'll pull this fan. The reason these switch mode power supplies are so awesome compared to old school linear supplies like that one is that this is switching at a much higher frequency. So these transistors are switching on and off, goes through this transformer, gets rectified, and these capacitors, because there's such a fast rising pulse, these capacitors don't have to provide much energy. Remember, these are like filter capacitors or reservoir capacitors. They're like little buckets providing energy as needed. And it doesn't take a lot of capacitance to do the job when your switching frequency is so high. That is only 120 hertz. So that's why I need all of these capacitors so that when I have intermittent power
surges, sags, it can provide that energy. This does the exact same thing. So what happens if we load this linear power supply down? What does the output waveform look like? That's what we're gonna do right now. So I've got my multi-comp active load here. I'm gonna load it down to 25 amps, 30 amps, and we'll see what happens to the output voltage over here, okay? Let me just connect this up real quick. Got my load connected to the output of my power supply over here, and we're monitoring it on channel 1. So let's go ahead and turn it on. 5 volts per division. Okay, so we're 13.8 volts output. I'm gonna turn my load on. See, we've got 13.8 volts there. So our Zener regulator is doing its job. Now I'm gonna give it a load of 5 amps. Turn that on. Draw on 5 amps. We're still at about 13.6 volts, so the Zener is still doing its job. Now I'm gonna give it, let's say 10 amps. Drop down to 13.4 volts, but that waveform still looks okay. 13.8 volts, down to 13.2. You can start to see some ripple there. So let's change over to AC and we'll take a look at that ripple. And we're gonna zoom in. Look at that, we're starting to see some wiggle there. Let's go ahead and say 25 amps. We have a lot more. So we're looking at 200, 240, 600 millivolts. Yeah, about 600 millivolts of ripple there, which isn't all that bad. I'm zoomed in pretty close. Let's give it 30 amps. I don't think we can get there, but let's try. Yeah, same, and we're down to 9 volts, so it can't quite do the 30 amps. But you get the idea.
So the next application we're going to look at is using capacitors as AC coupling, or we could call them DC blocking capacitors, right? Because that's exactly what's happening. So when we set up a transistor amplifier, we basically have, in this case, a voltage divider bias. It's a common emitter amplifier because the emitter is going to ground, and we have this collector resistor up here as our load. Now that will feed the next successive stage of the next amplifier. So the reason that we have multiple stages is if you were to have a single stage amplifier, you run into a lot of issues with oscillation, and your gain will be too high. You'll get all kinds of noise and weird stuff happening. So by breaking your wanted gain up into several stages, you can control the impedance better, you have a lower noise, you can feed back the signal back to the input, and you can control your gain a lot more effectively. But what you don't want to happen is you don't want the DC conditions from one amplifier stage influencing the other. Okay, so we set up a Q point, a bias point for this transistor at DC potential. And if we were to feed that DC into the next stage that we calculated all those resistors for perfectly, right, we would have a problem. So in a single-ended amplifier like this, we use these DC blocking capacitors in between stages. And you'll see them on the input here as well, okay, because we may be connecting something to the outside world and we don't know what that might be. It might have a DC bias on it. That could be dangerous for this transistor, so we put a capacitor there. Same thing on the output. If we're feeding something else, we want to make sure that we're not, setting our collector emitter voltage to the next thing that we're connecting it to, like a guitar pedal. We don't want to feed a DC voltage into the amp, though it should be protected already. We want to make sure that we take care of it on our side. Okay. Now this is of course effective at audio frequencies as well as radio frequencies. So I have an application on the bench over here. It's a UHF 100 watt amplifier, and it uses this technique to isolate stages between the preamp and the output stage. So let's take a look at that.
All right, let's take a look at this VHF amplifier. I actually bought this because I wanted to bounce signals off the moon, but then it turned out that I can't use that power level here in Florida because there's a lot of aircraft flying around, spaceships, that kind of thing. I've actually never been in here, so this should be interesting. Oh, all right. I'm going upside down. So this is the part that I wanted to look at. So you can't see the entire thing, but I just wanted to focus on a couple things here. Our RF signal comes in over here, okay, along this big fat trace and feeds into the base of this MRF 644. That is an RF transistor, power transistor. We've got all these little capacitors over here that help decouple the signal, and then it goes all the way over here through this feed-through capacitor, and this is what separates the Class A stage from this final stage, okay? This comes in through this, gets split off here. We have these two MRF 648s, okay? That signal goes off to the base, and this acts as kind of like a push-pull, and the output goes out to the coax. And so this capacitor is really what keeps each stage safe so that their DC bias points don't interfere with each other. I just thought it'd be cool to take a look at that.
So the next application we're going to look at is bypass capacitors. And just like the name sounds, we're going to use those capacitors to bypass some component. And we know that as frequency goes up, as this signal travels through this capacitor, the capacitor looks like a lower and lower resistance. As the frequency goes down, it looks like a higher and higher resistance, or impedance if you want to look at it that way. And we can use that to our advantage. So let's take a look at, this is a circuit for an LM386. And if you've been around electronics a while, you know that this is a fairly popular IC. It's been around forever. And we can use it as an audio amplifier. So it's kind of like a higher powered op amp. I mean, by high power, I mean like 100 milliwatts. And we can also connect a speaker directly to the output, which is pretty convenient. So let's look at the stages here and look at how we're going to use these bypass capacitors to do something. We're going to use them to increase the gain. So out of the box, without any external components, we can connect a power supply, input signal, and some stuff on the output in a speaker. And we have a very basic audio amplifier with a fairly decent gain. If we want to increase the gain, there's some things we can do. Let's look at the stages here real quick. So just like a standard op amp, we have some form of a differential input stage. Okay, in this case, it's older technology, so we're using BJTs, bipolar junction transistors, most of them PNP here. We have our inverting input, our non-inverting input. Okay, those get fed into the base of these guys. We have a current mirror down here. Okay, that forces the current in one leg to be the same as the other. So let's look a little bit more at this amplifier stage. So we have our differential pair. We're pulling the signal off of the collector here and driving this voltage amplifier stage. And that, of course, we have this bias spreader, and that feeds this push-pull circuit that drives our speaker. Attached to that is this feedback network. So we just have a couple of resistors that feed the output signal back to the input. That helps linearize things, control the bandwidth, and helps linearize the amplifier. So these two resistors control how much gain we have. Okay, now by default, this is set inside the integrated circuit, but they give us these pins that we can use to manipulate what's inside the chip. So again, if we add a capacitor here across these two terminals, then we can further increase that gain. If you look in the data sheet, I think if you bypass, you end up with a gain of like 200 instead of 20, which is kind of common. So you're bypassing components using the proper value of capacitance, and we have a bypass capacitor. So it just so happens that I bought a couple of these LM386 amplifiers online, and we can take a look at that on the bench, plug it in, and see if it works.
So here's a little bit of a close-up of the LM386 amplifier board. We have a potentiometer here that's part of the gain control circuitry. This obviously sets the gain. This is the output for the speaker terminals, and this is the DC voltage supply. So we have a capacitor here that is part of the output network for the speaker. Okay, so that blocks the DC from getting to our speaker. And we have all of our components down here that set up the gain. This guy is part of the DC decoupling capacitor. So we got a large value cap there just for safety. And yeah, you can see all the other resistors and capacitors that are part of the gain. Nothing connected to the top side here, so we're not manipulating that feedback loop like we looked at earlier. But let's give it a listen.
A dual measurement. However, as this not at all annoying relay tells us, the meter is switching between voltage and current. It is not measuring simultaneously.
Sounds like our friend James Lewis.
The switching is probably fine. Also notice the common input is shared.
All right, it looks like she works. Not the best sound quality, but pretty amazing from a little 8-pin IC. You can see why it was so popular.
I'd also like to take a look at this condenser microphone. So as you probably know, condenser is also another word for capacitor. And if we open this guy up, there's all kinds of interesting stuff in here. We'll take a closer look on the bench. But our microphone element here is actually a capacitor. So it has a metallized film on the front and a back plate. Okay, I think I have it backwards. Yeah, metallized film on the front. And those go down to an amplifier and this differential circuit that plugs into your recording gear. So before we look at this, let's just take a quick glance at the schematic. So here's the schematic as best as I could reverse engineer it. I understand that this circuit is called the Schup's circuit. So it takes a single-ended signal and turns it into a differential signal to send over a long cable run, right? So we have our actual condenser here, that's our capacitor, and we need to provide a high voltage, relatively high voltage, on those two plates of the capacitor in order to be able to measure or take that analog signal and further amplify it. Most condenser microphones need 48 volts, and that can be provided by what's called phantom power from a source that connects over the microphone cable over here. So most microphones need that 48 volts, and that comes from a separate supply. I happen to have it in my preamplifier, and that rides along the AC signal on the cable and can be picked up and pulled out here in this circuit. So the way they're doing it here is a little strange. So they're taking the phantom power, that's 48 volts already, they're taking it into this circuit, then they're using a Zener regulator to get 6.3 volts from it, and then they're using their own boost converter. Okay, so there's a lot of capacitors in there to provide that 48 volts that the condenser needs to build up a charge on its plates. Now, when it has that charge on its plates, we have this 1 gigaohm resistor here, and that helps maintain that charge. So when we speak, it moves that the diaphragm, on one side, and then actually changes the capacitance, which changes the voltage. Now we use a capacitor to block that high voltage DC and just let the AC signal pass through to this JFET. So JFET is a nice low noise solution, not so common nowadays, but it works well in microphone applications. So whatever this phase is here, this JFET also acts as a phase splitter. Okay, so it takes one side of that signal, flips it around backwards, so now you have a differential audio signal. Okay. Then we feed that through to a couple of NPN transistors, okay, and that just amplifies it even more. And it actually, the AC signal rides out along this XLR connector over to our preamp. So anyway, here we have AC coupling, we have blocking, we have bypass capacitors, in this section here. So everything's kind of right here. This is a great example of capacitor application. So now that we understand the schematic a little bit, let's go over and take a look at the actual microphone.
All right, now this is what I was really looking forward to, taking apart this mic. So this is a Shups design, a Shups schematic, and it takes your single-ended signal and turns it into a differential signal to send over your cables over long distances. So this is actually, from what I understand, I don't want to touch it, it's a piece of film, and then they gold plate it. So they deposit a thin film of gold on there. And then you see all these screws, that connects to a back plate. So this actually forms a capacitor. Not really sure what the post is there. Didn't get a chance to look that up. But what's interesting about this, you have the 2 wires that come from those 2 plates, all right? And like we saw in our schematic, that feeds over to this capacitor, which makes its way over to this little JFET right here. And I think one of these high value resistors here is, let's see, I think that says 1 gig. So that is what keeps the charge on this, these 2 plates of the capacitor and allows it to do its thing. And you can hear the Element 14 mascot barking in the background. So what's also interesting is they've conformally coated this with, you can see kind of a shimmer there. And I think anytime you have low noise stuff like that JFET amplifying with a large gain, you want to keep, the grit and grime out of there. A lot of symmetry here. So we've got some capacitors that we saw in our schematic that are part of these 2 common emitter amplifiers. And let's see, we have our Zener that helps regulate the voltage. And then we have this 6.3 volt Zener down here. Okay, that sets that voltage up for the rest of the circuit, the transistors to operate at. And this is the filter capacitor for it. R7 sets the current through that Zener. And then we have a bunch of, this is actually a boost circuit. So it takes that 6.3 volts and bumps it up to 48 volts. Now it can do that because we don't need a lot of current to keep a charge on this. Okay, we just need a high voltage. So there's not a lot of current being consumed there. And these 2 inductors here are just to keep stray, I believe, RF from getting into our circuit or, anything that we pick up from projecting it down the line. So that's about it.
So the last thing I want to talk about is decoupling capacitors. So here's a circuit that I was just going to play around with and kind of show how things work. Typically in any circuit you have a power supply and you have some maybe digital device or analog op-amp or something that performs some function. And there could be noise and ripple on the power supply. There are a lot of other circuits connected to that same power supply typically. And that can introduce, these fast transient signals can introduce harmonics noise on the line, as well as, the power supply itself could inject noise into the system. So it's a good idea to have a decoupling capacitor that is basically shunts across the power supply as close to the power pins of whatever device you're trying to protect. That way, that high frequency noise, remember it has a fast transition from low to high, high to low, and that will look like a short circuit. The capacitor will look like a short circuit to that fast signal. Okay, steady state signals like a DC power supply won't be affected by it, right? So typically you'll have values of 0.1 microfarads for those high frequencies. Does it need to be 0.1 microfarads? No. It does not. In fact, it could vary based on what you're doing, but a general good rule of thumb is to use 0.1 microfarads or 100 nanofarads. There was a shortage a while back, but you could use different values in parallel, like 0.22 mic in parallel. You'll often see sometimes a 1 microfarad capacitor or even larger in parallel with that. So the 0.1 mic capacitor will handle the really high frequencies, and the larger value capacitors can actually handle some of the low frequency stuff that you might see like noise injected from the power supply. So it's not uncommon to see that. I had an idea how to demonstrate this, and there are a couple of really good examples online that kind of are parallel to what I was trying to do here. So I actually made 2 of these boards. So this is an astable oscillator made from 7400 logic. And this is the second board that I made, and I destroyed it. I guess I shorted something out while I was probing around or something. So unfortunately, I can't demonstrate that. It's a good thing to keep in your bag of tricks. Sometimes schematics don't show the bypass capacitor, but it's an important part of any digital circuit or even analog stuff. So let me just grab a board and I'll show you. So here's a good example of a development board that has a lot of bypass capacitors on every supply pin around this integrated circuit. Usually there'll be multiple supply lines going to a microcontroller, and each one needs their own decoupling capacitor. The point is to keep the capacitor as close to the supply pins as possible. So usually you'll have like a ground plane, and then your positive supply traces will be on top or in the middle of the board. So you're going to want to connect one side of the capacitor as close to the positive rail as possible, and directly stick a via into ground if you can. Okay. Sometimes with BGAs you'll see decoupling caps all over the back. Anyway, that wraps it up for decoupling capacitors. All right, well, that does it for this episode of DC to Daylight. I hope you enjoyed this video on capacitor applications. It's always fun to tear things down, do these little micro teardowns. In fact, if you thought it was fun, let me know down in the comments if there's anything that you want to see me take a little bit of more of a deep dive into. I can certainly do that in future videos. Okay, so if you want to interact with me, you can do so down in the comments below. If you want more of an opportunity to engage and exchange pictures, schematics, things like that, you can, of course, join the Element 14 community. The link is down below, and I will see you there. Have a good one.